Hello everyone, welcome back to the session. So in the previous session, we discussed on general to specific ordering of a hypothesis, find-test algorithm, and also we have seen the relationship between your hypothesis called as a more general than or equal to relationship. We shall discuss in this session on version space and also very important algorithm, that is least then eliminate algorithm. Let's start the session. So in this concept learning, that is we have the second approach to the concept learning, that is candidate elimination algorithm. This algorithm will try to address some of the limitations of find-test algorithm. Here you know that find-test algorithm will output a hypothesis from H, that is from the set of H, which is consistent with the training example. So you may have many hypotheses in H, but only one of the hypothesis that might be fit the training data. So the key idea in the candidate elimination algorithm is to output a description of set of all hypotheses consistent with the training example. So we shall see the definitions first. The first definition is your consistent. So what do you mean by consistent? Say if I have an hypothesis H, which is said to be as a consistent with a set of training examples D, if and only if your H of x is equals to C of x, which means that the hypothesis which is defined over instances has to make sure that this hypothesis will satisfy or will classify your instance based on your target value. Means it has to classify positive as a positive instances and negative as a negative instances. So if this is so, that is H of x is equals to C of x, then we say that your hypothesis is consistent with the D, and this is how we represent with the notation. But getting into the actual definitions, we shall see the difference between the two major keywords here. One is consistent, and you have another definition called as, another keyword called as satisfies. So here you have two major keywords are there. So when we say that that instance x satisfies the hypothesis when H of x is equals to 1, which means that any of the hypothesis which tells that hypothesis meets all the constraints of your instances, then we tell that that hypothesis is satisfied with respect to x, and it is denoted as H of x is equals to 1, whether this instance may be a positive instance or negative instance. So that is not considered with this satisfies definition. But whereas in the consistent, here you should remember that any of the hypothesis which is defined over x has to classify based upon your target concept. So this is the condition. I hope this difference you have understood. Next we shall see the basic definition of version space. Now we shall see the next definition, that is version space. So remember, the candidate elimination algorithm that represents a set of all hypotheses set of all hypotheses which are consistent to your observed training data. Assume that here your set of all hypotheses, which is denoted as H, and these hypotheses are derived, or these hypotheses are consistent with your instances. So here you have xn. So every hypothesis is consistent to any one of the instances. So what do you mean by version space? Version space is nothing but denoted as Vs with the subscription H comma D. So what this version space consists of? This version space consists of all the or subset of all the hypotheses in H. So this is called as version space with respect to the hypothesis space and the training example D. This is your training example, and also this is your H, because it contains all the possible versions of target concept. Now we shall see the definition here. What the definition says, that you have a version space which is denoted as Vs with the subscription H comma D, which says that V version space with respect to hypothesis space H and training example D is a subset of hypothesis from H, which means that you have a hypothesis set in the version space, but these hypotheses are from your H, which are consistent with the training examples that are in D. So this is your definition of version space. I hope you have understood two basic definitions. One is a consistent and another is version space. Now let's see the algorithm. Here the algorithm is least then eliminate algorithm. So this algorithm will initialize the version space that contains all the hypotheses in H, and then eliminates any of the hypotheses found inconsistent with the training example. And this is your algorithm, which consists of 3 steps. As you know that you have a version space which is denoted as Vs version space H comma D. What it consists of? It consists of a hypothesis. Where these hypotheses are derived, these hypotheses are taken from your H. So H is nothing. What this H consists of? H consists of all the, or it consists of a hypothesis which are consistent with your training data D. So what this version space consists of? Version space is a subset of this H. It is a subset of H. So what this list and then eliminate algorithm will do? Whatever the hypothesis in this version space are there, it will make sure that whether each and every instances that is represented as X, your capital X, here every instance are represented in capital X. So you have to remove any of the hypotheses which are not consistent with the hypothesis. Assume that this is your H1, H2 and H3. How many instances are there? 3 instances: H1, X1, X2, X3 and X4. Assume you have 4 instances are there. So here assume that H1 is consistent with only with respect to X1, and remaining 3 instances are not consistent with the hypothesis 1. So what you have to do? You have to remove this H1 from your version space, because it is not consistent with all the training instances or examples. So assume that H2 is there. H2 is consistent with only X1, X2 and X3. So it is not consistent with X4. So H2 is not consistent with your X2, which is denoted as H of X4 is not equal to C of X4. So assume that this H3 is consistent with all the instance, that is X1, X2, X3 and X4. So only this H3 is kept in your version space, and the remaining H1 and H2 is removed from your version space. So this is your least then eliminate algorithm. Let's see the next representation, which is more compact representation for your version space. So previously, the candidate elimination algorithm, which works on the same principle as your least then eliminate algorithm. So what this version space is represented? It is represented by its most general and least general members, and these members form a general and a specific boundaries, that is of sets that delimits the version space within the partially ordered hypothesis space. So assume that you have a version space with respect to the candidate elimination algorithm. So in this version space you have some sort of a hypothesis, but here you have one set of boundary, that is we can call it as a specific boundary, and here you can say that is a general boundary. So these are the two boundaries of your version space, so which will delimits your version space within the hypothesis space. So by using these representations, now we shall see the definition of a general boundary. What the general boundary says that here the general boundary, which is represented by G, which is defined with respect to hypothesis space H and the training data D. What it consists of? It consists of a set of hypotheses which are consistent with D. But what these hypotheses are? These are maximally general member of set of hypotheses. So this is how we have defined your boundary called as general boundary, and this is the notation. And we have the next definition called as a specific boundary. Again you can see here specific boundary, which is defined with respect to hypothesis space and training data D. What it consists of? Again it consists of a set of hypotheses which are maximally specific members. Each and every hypothesis are maximally specific members of H. Again you can see H is again a set of hypotheses. So these are the definitions of general boundary and specific boundary. See, in this diagram you can see a set of hypotheses, that is a version space which is defined with respect to your hypothesis space and D. What it consists of? It consists of 6 hypotheses. Here you have 2 hypotheses, 1, 2, 3, 4, 5 and 6 hypotheses are there, which means that this version space consists of 6 hypotheses. So this version space shows you the two boundaries are there. One is general boundary and another is your specific boundary. I already said that what this general boundary consists of. Again, it consists of set of hypotheses which are maximally general members of your hypothesis. And here you have another boundary called as S. Again, it consists of a set of hypotheses which are maximally specific hypotheses from H. So these are the two boundaries that what we define. So these are derived based upon your concept learning called as Enjoy Sports concept learning. We shall see the candidate elimination algorithm in the next session. Thank you so much.